Have you ever wondered what actually stops an airplane from flying straight up into space? As an aerospace engineering student, the SR71 Blackbird is my favorite aircraft, famous for flying incredibly high and fast. Today I'm going to show you how to calculate the maximum service ceiling of an aircraft, specifically the SR71, using just basic algebra and the fundamental lift equation. The first step is going to be to define a coordinate system so we can keep our bearings straight. Following that, we're going to label our force upwards, which is going to be the lift on the aircraft, and we are going to label our force downwards, which is the weight of the aircraft being acted upon by gravity. We then sum up our forces in the y direction, where we have lift minus weight equal to 0, since there is no change in altitude within this scenario. We can then define that lift equals weight, where lift, L, is equal to 1/2 rho, the density of the air, v squared, which is our velocity, times s, which is surface area of the wings, times cl, which is our coefficient of lift. And because L equals W, we can then define W equal to the same formula, 1/2 rho v squared s c sub L. The secret to an aircraft's flight ceiling is the air density rho. As you go higher, the air gets thinner. There is a specific altitude where the air becomes too thin to support the plane's weight, so we can solve for rho. We'll simply divide the entire left-hand side W by 1/2 v squared s c sub L, rearrange, and solve that rho equals 2W over v squared s c sub L. Now we reference our known data about the SR71, where we have a flight weight of 440,800 newtons, a flight velocity of 950 meters per second, which is just about Mach 3.2. We have a wing area of 167 square meters. And finally, we have a coefficient of lift of 0.17. We can then plug all these numbers into our equation we just derived, where we have rho equals 2 times 444,800 divided by 950 squared times 167 times 0.17. Running those numbers in a calculator, we'll end up with an air density rho equals 0.0347 kilograms per meter cubed. The final step is to reference our NACA standard atmosphere tables, where we can then confirm that our 0.0347 kilograms per meter cubed is approximately the density of air at 83,600 feet. This is a fantastic result, as it perfectly aligns with the recorded real-world data, because according to the Evergreen Aviation and Space Museum, the SR-71 Blackbird's operational cruising altitude was documented at being just above 80,000 feet, which is about what we calculated. So the next time you look up at the sky and see airplanes, remember that the limits of flights aren't just guesswork. They are boundaries defined by physics, and with a single equation, you can find exactly where the sky ends.